Welcome back. Today we're diving into the life and work of Michael Green, the 18th holder of that prestigious Lucasian chair. You might know him best for his work in string theory.
Yes, specifically the first superstring revolution.
Right, the first superstring revolution. To grasp how significant his work is, though, we need to remember what string theory is all about.
Exactly. At its core, string theory aims to bring all forces of nature together.
Including gravity.
Right. Gravity, which has always been a bit of an oddball in traditional quantum mechanics.
That's where Michael Green's work comes in.
It really does. His work tackled a problem that was really plaguing string theory. And it helped make string theory a stronger contender as a unified theory of everything.
And that problem was?
Anomalies.
Anomalies.
Yeah, for years, string theory struggled with these things called anomalies, these inconsistencies that just pop up in calculations, and they threaten the entire foundation of a theory.
So like trying to build a house with a blueprint full of errors.
Yes. It just wouldn't stand.
Okay, see. That's the kind of threat anomalies pose to string theory. So how did Michael Green solve this problem? What was his groundbreaking contribution?
Well, Green, along with his collaborator John Schwartz, discovered what we now call the Green-Schwarz mechanism.
Okay.
A way to cancel out a specific type of anomaly in type I string theory. This type of string theory is interesting because it includes both open and closed strings.
Adding another layer of complexity.
Exactly. So essentially, they found a way to fix the blueprint of string theory.
Making it stronger.
Eee!
And more capable of describing the universe.
Exactly. And the fix, it wasn't just some random patch. It required a very specific mathematical condition related to something called a symmetry group, specifically SO32. Now, for anyone listening who's not a physicist, symmetry groups essentially describe the inherent patterns and structures within a theory. The Green-Schwarz mechanism showed that for this particular symmetry group, the anomalies just amazingly canceled out.
Wow. That must have been huge for string theory. How did this change research in the field?
Well, it sparked what's now known as the first superstring revolution. Before Green and Schwartz's work, lots of people saw string theory as just this beautiful mathematical framework.
Right.
Too abstract to be a real description of the universe.
Okay.
But their discovery, it made the theory so much more credible, mathematically sound, and it opened up so many new research avenues.
Can you give us an idea of how the Green-Schwarz mechanism actually works?
Sure. It basically involves adding what's known as a Chern-Simons term into the mathematical framework of string theory.
Okay.
This term just elegantly counteracts that troublesome anomaly.
It restores balance to the equations.
Yes, exactly. Think of it as adding a counterweight to stabilize a system.
This is all during his time at Queen Mary College, right? Before the Lucasian Professorship.
You're right. He was a professor there from 1978 to 1993 before returning to Cambridge. But Green's work went beyond just the Green-Schwarz mechanism.
Oh, right. His work on Dirichlet boundary conditions.
Right. These boundary conditions basically define how strings can behave at the edges of space-time.
So what are some of the implications of that?
Well, it led to some crucial concepts, like D-branes.
I've heard of D-branes.
Yeah.
But honestly, I need a reminder. What are D-branes? Why are they so important?
Okay, so imagine open strings, like tiny pieces of thread, just floating in space-time. D-branes, which is short for Dirichlet branes, are surfaces where these open strings can attach themselves. They're like multidimensional membranes within space-time.
So it's not just strings vibrating in empty space. They're interacting with these D-branes.
Yes, exactly. And that interaction adds a whole new level of complexity and possibilities within string theory. These D-branes, they can have different dimensions, from point-like particles to higher dimensional structures, which really enriches the landscape of possible universes that string theory can describe.
Wow. So not only did he help solidify string theory's foundation, but he opened up pathways to explore these new concepts. It's really quite a legacy.
It is.
Now I understand why he ended up in such a prestigious position.
Absolutely. He was confirmed as the Lucasian Professor in 2009, following Stephen Hawking. And he held the chair until 2015. Quite a lineage.
It really is. Speaks volumes about his contributions to physics. Before we get into his time as the Lucasian Professor, let's rewind a bit. Where did this all begin?
Well, his story starts in London, where he was born in 1946.
Post-war London. A time of rebuilding. Where did his academic journey begin?
He attended William Ellis School in London, and then it was up to Cambridge.
Cambridge. So much scientific history there.
You can practically feel the weight of history in those halls, and Green thrived there. Graduated from Churchill College, Cambridge, first-class honors in theoretical physics in 1967.
First-class honors. Exceptional.
Absolutely. And he continued his studies at Cambridge, earning his PhD in elementary particle theory in 1970.
So even in his doctoral work, he was already focused on the fundamental building blocks of the universe.
It seems that way. After his PhD, he went on to a series of postdoctoral research positions, first at Princeton University, then back at Cambridge, and then the University of Oxford.
Princeton, Cambridge, Oxford. What an amazing opportunity to be part of those communities.
Must have been an incredibly stimulating time for him. During those years, he really refined his skills, delving deeper into quantum field theory, laying the groundwork for his later breakthroughs in string theory.
So we have Michael Green, PhD from Cambridge, postdoctoral experience from some of the top universities in the world. What happened next?
In 1978, he joined the faculty at Queen Mary College, University of London.
That's where I left off. That's where he spent the next 15 years working his way up to professor, right?
Yes, that's right. And it was at Queen Mary College that his collaboration with John Schwartz really took off, leading to that big breakthrough we were talking about earlier.
Right, the Green-Schwarz mechanism.
Yeah.
Do we know anything about their collaboration? What was it like in those early days?
Well, they were known to spend countless hours just discussing, working through complex equations, challenging each other's ideas. It was a true partnership, driven by their shared passion for uncovering the secrets of the universe.
Their dedication and collaboration led to a major turning point in theoretical physics. It wasn't just about one discovery. It was about a whole new way of thinking about the universe.
You're absolutely right. It paved the way for further exploration into new types of string theory, the concept of D-branes, and just a deeper understanding of reality itself.
It's remarkable how one collaboration can have such a huge impact.
It really is a testament to scientific inquiry, collaboration, and that relentless pursuit of knowledge.
Now, after all that he did at Queen Mary College, did he ever go back to Cambridge?
He did. In 1993, he was appointed John Humphrey Plummer Professor of Theoretical Physics at Cambridge.
It seems fitting that he would return to where his academic journey began.
And it was back at Cambridge that he continued to make really significant contributions to string theory, cementing his place as a leader in the field.
And then, in 2009, he was appointed to the Lucasian Professor of Mathematics at Cambridge, succeeding Stephen Hawking.
It's a position that has been held by some of the most brilliant minds in history, which really shows the impact and influence of Michael Green's work.
To follow in the footsteps of giants like Stephen Hawking and Isaac Newton is incredible. It's a testament to a lifetime dedicated to pushing the boundaries of scientific knowledge. What a journey. From those early days as a student at Cambridge to holding the Lucasian chair.
His story is really inspirational. Profound discoveries often start with a spark of curiosity, challenging conventional wisdom, and the perseverance to explore the unknown.
And his journey didn't end there. After serving as the Lucasian Professor, he continued his research and shared his knowledge, mentoring new generations of physicists. His impact is far beyond just his own discoveries.
Absolutely. He's played a huge role in nurturing the future of physics, ensuring that the search for knowledge, the pursuit of a unified theory, continues.
Now, reflecting on his life and career, I'm curious about the impact of that first superstring revolution, the period of intense activity and excitement sparked by his work with John Schwartz. How did the Green-Schwarz mechanism influence how string theory developed in the years that followed?
It's a great question. It gets to the heart of how science progresses. The Green-Schwarz mechanism wasn't just about solving a problem, you know? It opened up all sorts of new possibilities. It was like a catalyst that pushed the field forward in unpredictable ways.
So it was a turning point. It redefined how string theory research was done.
Exactly. New ideas explored, new connections made, and suddenly that dream of unifying all forces of nature felt closer than ever before.
Must have been electric for the physics community. Did the Green-Schwarz mechanism lead to other breakthroughs? Did it open up entirely new lines of inquiry?
Absolutely. For example, it led to the development of new types of string theory, including type 2 string theory, which Green co-discovered with John Schwartz. It wasn't just one isolated discovery. It was a foundation for a whole new framework of theories and concepts.
It's amazing how far string theory has come. And it's clear that Michael Green's work was instrumental.
It was crucial. He was a true pioneer in the field. And his legacy continues to inspire physicists all over the world.
Now, before we wrap up this part of our deep dive, I want to touch on something you mentioned earlier. Michael Green's work on Dirichlet boundary conditions in string theory.
Right. That work was so important for concepts like D-branes, which are central to how we understand string theory today.
Remind us what D-branes are and how they fit into string theory.
Imagine a universe where strings are the fundamental building blocks. These strings, they can be closed loops, like tiny rubber bands, or open strings, like little pieces of thread. D-branes, or Dirichlet branes, are surfaces where those open strings can end.
So the D-branes are like walls or membranes in space-time, and the open strings can attach to them.
Exactly. And these D-branes can have different dimensions. They can be a point, like a zero-dimensional dot, or a line, a sheet, or even higher dimensional.
So instead of just having strings, we now have these D-branes that they interact with.
Exactly. This adds a whole other layer of complexity and richness to string theory. It allows for a much wider range of possible universes, each with different properties and different laws of physics.
So Michael Green's work on Dirichlet boundary conditions opened up a whole new realm of possibilities for string theory.
Absolutely. It was a crucial step in developing D-brane physics, which is one of the most active and exciting areas of research in string theory today.
It's fascinating how something as abstract as boundary conditions can have such huge implications for how we understand the universe.
It's a reminder that even the most theoretical concepts can be deeply connected to the physical world. But now it's time to move on to part 2 of our deep dive. We've covered a lot, but there's still much more to explore.
You're right. We've gone through his early years at Cambridge, his groundbreaking discoveries in string theory, and the impact he's had on the field as a whole. But the story doesn't end there. In our next segment, we'll dig deeper into the implications of his work and explore the broader questions it raises about the nature of reality and the limits of our knowledge.
So we were talking about how Michael Green's work on those Dirichlet boundary conditions and then all the work on D-branes, well, it really opened up a new chapter in string theory.
Yeah, those abstract boundary conditions. It's amazing how they led to such significant developments in our understanding.
It really shows how everything's connected in theoretical physics.
Right, even a tiny detail can lead to a whole bunch of new insights.
Yeah.
I'm still curious about these D-branes, though.
Sure.
You mentioned they can have different dimensions.
Yeah.
What does that mean? Like, what's the difference between a two-dimensional D-brane and a five-dimensional one?
Okay, so think about how we experience the world. We've got 3 spatial dimensions, right? Length, width, and height.
All right.
So a 2-dimensional D-brane, it would be like a flat sheet, existing in those 3 dimensions, but with no thickness. Now, imagine you could extend that sheet into 2 more spatial dimensions that we can't see. That would be a 5-dimensional D-brane.
So these higher dimensional D-branes, they're in a realm we can't even experience.
That's the idea. String theory suggests that there might be more dimensions to the universe than we can perceive. And D-branes, well, they can extend into those extra dimensions, giving them properties and behaviors that we're just beginning to understand.
Like they're bridges to another reality, one we can't see.
That's a great way to put it. And their existence has led to some really interesting possibilities in string theory. For example, some physicists think that our entire universe could be one giant D-brane floating in a higher dimensional space.
So instead of just tiny strings, we're talking about huge cosmic structures.
Exactly. And the properties of those D-branes could determine the fundamental laws of physics in our universe. It's a pretty amazing view of the cosmos.
It's definitely different from the old view of particles in 3 dimensions.
Yeah, string theory with D-branes and all those extra dimensions has really changed how we think about what the universe might be like.
And Michael Green was a big part of bringing those ideas to light.
Oh, absolutely. His work on Dirichlet boundary conditions was essential for our understanding of D-branes and their role in string theory.
Now, I want to shift gears for a bit.
Okay.
We've talked a lot about his scientific contributions.
Right.
But what about Michael Green, the person? What kind of person was he? What drove him to pursue such a challenging field?
Well, people who knew him describe him as deeply thoughtful, intellectually curious. He was known for being quiet, having a sharp wit, and of course, that passion for uncovering the universe's mysteries.
It sounds like the classic image of a brilliant scientist, driven to understand the very nature of reality.
Definitely. And you can see his dedication in his career. He wrote tons of influential papers, mentored so many students who then made their own contributions to theoretical physics.
So not just a brilliant scientist, but a great teacher, too.
Absolutely. His impact goes way beyond his own discoveries.
A legacy that will last for a long time.
For sure. And it all comes down to his curiosity and dedication to pushing the boundaries of knowledge. You know, before we wrap this up, I want to talk about something else about Michael Green's legacy.
Oh!
Something that goes beyond any particular discovery he made.
I'm listening.
It's about how he shows the importance of challenging established ideas. For centuries, physics was all about particles.
Those tiny, indivisible particles.
Right, but then string theory came along and asked, What if it's not particles, but tiny vibrating strings that make up everything?
It was a huge change from how we used to think.
It was a total paradigm shift.
And Michael Green was right there leading the way, pushing the boundaries, opening up all these new avenues of exploration.
Exactly. His work on the Green-Schwarz mechanism and D-branes, well, it helped solidify string theory, made it a more likely candidate for that unified theory of everything. But even more importantly, it showed that our understanding of the universe is constantly changing, that we should always be questioning our assumptions and looking for new ideas, no matter how out there they might seem.
It's an important lesson, especially in a field as complex as theoretical physics. It reminds us that the pursuit of knowledge is an ongoing journey, and we should never be afraid to challenge the status quo and embrace new ways of thinking.
And that's a legacy that goes far beyond any specific scientific finding. It's that spirit of inquiry, that desire for knowledge, that willingness to face the unknown that will keep inspiring generations of scientists to come.
Those are inspiring words. Michael Green's journey, from his days as a student at Cambridge to his groundbreaking work in string theory, it's a testament to human curiosity, to that quest to understand our place in the cosmos. But as we've said, his contributions go beyond any specific discoveries. They've reshaped our understanding of what the universe might be, opened up a world of possibilities that we're only starting to explore.
Now, as we get to the final part of our deep dive, I think it's worth thinking about the bigger picture. What does his work tell us about reality itself? About how much we can actually know, and about what future discoveries might be out there, discoveries that could change everything we thought we knew about the universe? Those are the questions we'll explore as we wrap up our look at Michael Green's legacy.
It's been quite a journey exploring the life and work of Michael Green.
It really has. His impact on string theory is undeniable.
Especially the Green-Schwarz mechanism and his work on D-branes. They've really changed how we understand the universe.
Absolutely. But it goes beyond just the discoveries themselves, you know? It's about how he approached science, challenging the norms and exploring new ideas.
Right. He wasn't afraid to imagine a completely different kind of universe. One made of strings instead of particles.
And by doing that, he opened up so many new possibilities. He really pushed us to rethink what reality even is.
For such a long time, we thought of the universe as this collection of particles, interacting in 3 dimensions.
And then string theory came along, with extra dimensions and those tiny vibrating strings. It really changes your perspective.
It makes you wonder, if those extra dimensions are real, what are they like? Could there be other universes hidden in them? Other life forms we can't even perceive?
Those are big questions, ones that physicists and philosophers are still trying to wrap their heads around.
The fact that we're even asking those questions shows how influential Michael Green's work has been. He expanded our understanding, pushed the boundaries, and inspired a whole new generation to tackle those fundamental mysteries of the universe.
I think that's what makes his legacy so powerful. It's not just about what he discovered, but how he approached science. Always questioning, always open to new ideas, and dedicated to the pursuit of knowledge.
He showed us that understanding the universe is a journey, not a destination. A journey that requires intellectual rigor and a sense of wonder.
And that's a legacy that will continue to inspire scientists for a long time.
Well said. His story reminds us that science isn't just about finding the answers. It's about asking the right questions, pushing those boundaries, and embracing the mystery and the wonder of it all.
It makes you think, what other revolutions in physics are waiting for us? Maybe future generations, inspired by Michael Green, will uncover even deeper secrets of the cosmos, things we can only dream of today.
It's exciting to think about. And on that note, we wrap up our deep dive into the life and work of Michael Green, the 18th holder of the Lucasian Chair of Mathematics at Cambridge. His work on string theory, his passion for knowledge, they've truly left a mark on the world of science. Until our next deep dive, keep those questions coming, never lose your curiosity, and keep exploring the world around you.